First of all, thank you everybody for giving me this opportunity. It's a pleasure for me being here. And my name is Francesco Aldo Venturelli. I'm a second-year PhD student here in Pompeu Fabra University. I'm also visitor of the UPF Barcelona Supercomputing Center. And in this project, I'm basically working with all the guys here in the team. So with the huge help of Emanuele Costa, Chico Kat Krishnanuni, Bruno Julia Diaz, Miguel Angel Gonzalez Ballester, and Alba Cervera Lierta. So in this project, the idea of this project is a little bit, it goes a little bit far from physics. It uses the quantum annealer and the physics behind quantum annealer applied to a problem in artificial intelligence within the framework of explainability and interpretability of deep learning models. Okay, so to give you a little bit of the context, I need to explain you some part of the background, giving you some notions about the background in order to then get to the core of the project. So basically, supervised learning technique is one of the 3 techniques that we can have to perform deep learning or artificial intelligence algorithms. The idea is that you have set of data which are labeled, and you know a priori which is the label that these data belong to. And the idea is to construct some models that are trained in order to match the label and, for example, in this case, is the images that they are looking at during the training process. And you do this basically by calculating the gradient of a cost function, which embeds the actual solution of your problem. And by calculating the gradient of the cost function, basically you update some weights that then are retrieved. And in the testing phase, you basically generalize and you perform your prediction. I mean, the model actually performs the predictions. So despite the advantage brought in the scientific community by artificial intelligence models, some issues simultaneously have arisen. And one of these relies in the large framework of interpretability. So how much can we trust about basically model predictions, and are we able to actually explain what's going on and the reason behind some models' outcomes or model predictions? And this is it's a tough problem when you apply like machine learning models, especially for example in medical diagnosis. So you would like to interpret fairly the model's outcomes. So before getting to the core of the project, I need to give you a little bit of explaining you the model that we are actually inspecting with quantum annealer and the physics behind the quantum annealer, which is a convolutional neural network. Probably you already know what it actually is. But for those of you that do not know, basically convolutional neural networks is a model that is applied to video data or images data. In this case, we are applying to images. And it's composed by 2 parts. One is called the feature extractor, where we have sequences of convolutional blocks. And within each convolutional block, you have sequences of layers, of trainable layers, that basically extract what they're called the feature maps or the representations out of the data that they are looking at. And after them, there is a final part, which is a fully connected layer, which basically performs the predictions. I mean, compute the probability associated to each class that the data belong to. And basically, the important part relies in how good the model is able to extract the representation. So, because of course, if you try to think to a binary classification, where, for example, you want to distinguish the differences between cat and dogs. Of course, these kind of animals have the same features. Basically, they have ears, have nose, and so on. But if the model is able to capture class-specific and what they are called disentangled features, and not in the sense of quantum mechanics, your model is basically good to generalize and to make further predictions. So in the context of interpretability and explainability, we have several algorithms that basically try to highlight the part of the data where the model in this particular framework has looked at in order to recognize specific classes of images that they see. For example, in this case, we have gradient class activation maps, which is abbreviated to Grad-CAM. And basically, Grad-CAM performs a heat map. I mean, it highlights the region where actually the model paid a lot of attention and focused much more in order to generate the prediction that it actually does. So in this case, for example, it can distinguish the differences between cat and dogs. And for example, in the second picture, it says that the image that is looking at is actually a cat because it focuses on that part of the image which surrounds a cat. And then I have the details about how Grad-CAM is implemented. Maybe we can talk it later. But one of the problems of Grad-CAM is that, okay, it's a good method to highlight the differences and to inspect what the model is looking at, but the problem is that Grad-CAM actually doesn't select the most meaningful information, the most meaningful feature maps, or those that are class related. It gives an overview of the actual set of feature maps that are activated during the prediction. To give you an example, in order to clarify what I'm saying. So basically, there are a lot of situations where, for example, the model predict correctly an image, for example, but the features or the representation that is paid attention to come from, for example, the background. And of course, in object detection, we would like to avoid this, because if I want to recognize such an image or the subject of an image, why my model is is retrieving so much information from the background. So actually, this leads to the core of the project. I mean, we are trying to formulate what is called the feature selection algorithm in order to do with the annealer, in order to select a subset of the most meaningful feature maps that are extracted from a target convolutional block that to satisfy two constraints. So in this particular framework, so why we would like to use the annealer? Basically, there are some hints that that basically yields to this conclusion or to this suggestion. One of these is that feature selection algorithm usually, in general, can be NP-hard problems and also can be mapped to max-cut, where, for example, by extracting these representation out of a convolutional block, basically we have a fully connected graphs where each node is actually a feature map, but of course each edge adds its own weight, so it's not easy to find a solution of this kind of graph, where the solution is actually the solution of the max-cut associated to the feature maps that are extracted. Then again, we can reformulate and rephrasing this problem as a cubo problem, because we have we want to select feature maps that basically are constrained by satisfy two constraints. So in this particular case, we construct the cubo matrix where we want to, of course, maximize the linear term, which actually computes the positive gradient contribution of each feature maps. So basically the way that each feature map contributed to the gradient during the process of learning. And at the same time, we want to minimize the quadratic term, which basically represents how mutually orthogonal these feature maps are between each other. Or how much they are independent among each other. And this term basically is estimated by computing the cosine similarity among two vectors. One of the benefits of this kind of reformulation is that we all know that quantum annealer seeks to find a ground state solution of energy minimization problems. But in this particular context, with and in the frame of explainability, basically, if we get some solution which corresponds probably to some other, excited states, and they're not exactly the ground state, probably can also be valid in this kind of context, because we are just asking to sample the bit string of the feature maps that contributed the most to these two kind of constraints that our problem Hamiltonian has been set up. And the idea is that the bit string embeds exactly the set of feature maps that are more relevant to this kind of problem. So one of the things that I have to do of this project is that we basically analyzed each image of our data set, and each image corresponds to one Hamiltonian, and one Hamiltonian, of course, corresponds to one problem, so we have to set up the annealing procedure multiple times one time for one image at a time. And here is how we constructed the problem Hamiltonian, where basically we set up a strength factor beta, which makes the linear term more relevant with respect to the quadratic term or the opposite. Then we set up the couplings, which basically encode the cosine similarity among consecutive maps. The linear term, which is the positive gradient contribution. And then we use the linear scheduler, and we construct a global time-dependent Hamiltonian, which is composed by the driver Hamiltonian, which is in terms of sigma x, Pauli x operators, while our problem Hamiltonian is composed by number operators. So basically, the identity minus the Pauli z operator. So now I'm going to show some results. Of course, the simulation are actually in progress, so we have to refine and make the results more robust. And also we have to perform other kind of analysis more in the part of the explainability, because something interesting is coming out. So the first result that I would like to present, which basically does not give so much information with respect to the second one, but basically is how the minimum gaps between photostat state and the ground state scales. The frequency associated to each image. And the interesting thing that we can notice is that, as I said, for one image, we have one problem Hamiltonian, and so we have one linear procedure. Then we go to the second image, then the third image, and so on. So despite we have visual differences with respect to the images, because in this data set we have images of cats, dogs, ships, trucks, and so on. So they seem that on average, all these Hamiltonians have the same, or converge to the same spectrum. I mean, even they represent different objects, different images, where we can see the differences. They lead to some distribution, which is a little bit concentrated in the first part on the right of the non-closing gap. So despite the differences, we have that the Hamiltonian behave like the same in terms of the delta values. Then the second results that basically confirm and doesn't provide so much information with respect to the other, but also take into account the time. I mean, here we computed the two-dimensional histogram with respect to the delta value, the energy gap, and the time at which we got the minimum gap. So basically, it's concentrated on the final part of the annealing time. So this probably, is accumulated on the upper left side of the image. So probably here we should inspect other kind of scaling procedure, because here we set up the scheduler to be linear. I mean, we define S as each time step divided by tau, the annealing time. So basically, probably in this kind of context, we can go further. I mean, we can set up other kind of schedulers. Probably we can accelerate the annealer up to a point and then go adiabatically towards the final annealing time. And the last result, which basically constitute the code of the project, basically represent which are the bit string, which are the feature maps that are not correctly, but that are selected from the quantum annealer. And we perform also a small, a small comparison with what we got with simulated annealing, so with classical heuristic method. So to generate this plot, basically, once we have computed the annealing evolution, basically we can sample an index, which is converted to a bit. Probably it's not working. I'm too close. Hello? Sorry. Okay, sorry. So basically we compute, so after the annealing time, we sample an index, which is converted to its binary representation, and basically this binary representation represent the bit string, represent the actual bit string, which represent the actual selected feature maps for that kind of image. So for each image, we sample a bit string of the most informative feature maps or representation that the model has learned that, of course, satisfy the two constraints that we set up in the Cubo-Hamiltonian. In the Cubo-Hamiltonian. So in this way, so despite we have that some of the bars share two different colors, meaning that for different images that belong to different classes, we have the same set of features that are activated. I mean, the same feature map has activated. And this is something that we would like to avoid because, of course, we want our model to identify class-specific feature representation in order to distinguish the differences between the object, the data that they see. Also, we can see a lot of disentanglement. Again, it's not something like quantum entanglement. So it's a way to say that the feature map are distinguished, I mean, are different with respect to each other and are also class specific. And they're activated only when the model has seen these particular classes of images that you can see. And this is, of course, is an analysis, it's a sort of a post-processing analysis. So inspecting which are the feature maps that are activated. But the idea is that to perform other kind of simulation that goes in that direction. I mean, identifying the differences and why this happens. I mean, for example, differences, for example, why some feature maps are activated for objects that belong to different classes. And so on. And also one of the idea behind this plot is that we could also reframe the training process in a way that not only we want to minimize like standard cost function, which can be the cross entropy among the classes, but we can also put a term which informs the model to catch some class-specific representations for each of the image that is training onto. This is the orthogonal matrix. So of course, in this kind of matrix, if we have the identity, basically we're happy because of course all the representation are distinguished among different classes. And now I draw my conclusion. So again, as I said, we have to increase the simulations. We have to inspect other part of the project. We would like to perform some scalability simulation in order to increase the number of feature representation that are extracted from a target convolutional block in order to see how the annealer behaves when we include larger number of inputs. But then in this project, we have proposed basically this method that perform this analysis on representation that are extracted directly from convolutional blocks and learned during training. So we are working also for making a paper of this project, and I mean, thank you for the attention. Yeah, thank you very much.
We have plenty of time for questions. Thanks for keeping to time. Do you have anything? Oh, you're just helping with the mic. Okay. Anyone have any questions? Oh, yes, back there. Yes. I can go either way.
Thanks for this very interesting talk. Could you go one slide back before the conclusions? No, right before the conclusions.
Sorry.
Yeah, it was a correlation. This is a correlation an overlap matrix.
This one?
Yeah.
Yeah.
I wanted to ask, do you understand because I get it, it looks quite okay, but I saw like dog and car have a 0.54 overlap. Is this something you would expect on your feature selection? Car, yeah.
You mean dog and car? I mean yes. This is the. I mean, basically this is the interesting part. So because of course. Okay, I should have said a lot of things more because, of course, how the model has been trained also is something that, of course, is relevant because of also if the model goes overfitting or if the model is not trained well, so there can be misleading results. But in this case, for example, basically, when the model extracted the feature maps and we forced the feature maps to be inside the range, here we just chose like 16 feature maps extracted from the last convolutional block, which is the one right before the predictor. Basically, we can have, feature representations that are activated, but that belong to different classes, but that are the same.
Okay.
So. And this is exactly the problem that we would like to solve. Basically, we would like to create more interpretable models that can also distinguish among or can activate feature maps that are class specific. Because otherwise, this can make could be a little bit misleading because if your model activates some representation when it sees different images, but that belong to different classes, but the representation that are activated are the same, this could lead to some very wrong results, or it could be problematic, of course, because you have to distinguish between, binary classification where the importance to distinguish between the classes is very important. So
I actually have two more questions.
Okay.
Could you go back to slide 9? Yeah, here, yes. When you were explaining about the strand factor, I'm guessing, do you have are these constant for every image that you work with?
As I was saying, we have to perform additional simulation because here we set up the value of beta to be constant, but of course we have to vary it between, of course, 0.1 and 0.9, or you can go also, you cannot go 1 because otherwise one of the term is 0. So this basically scaling factor makes the linear term or the quadratic term more relevant with respect to each other, while Jij basically computes the cosine similarity between the two feature maps. You have to think that the feature maps or the representation that are extracted from the model are basically vectors. And so you want to compute how mutually orthogonal these two vectors are. And of course, if you have 0, so if you have the cosine similarity 0, that means that the vectors are independent. The feature maps are independent with respect to each other. So in this particular framework, we are basically, we want to extrapolate, we want to subselect the feature maps that highly contribute positively to the gradient and the ones that are mutually orthogonal with respect to each other. But there is also another framework which penalizes the orthogonality. So we want to find a fixed number of feature maps which gives a positive contribution to the gradient, but they are highly correlated, are highly similar, because this leads you aggregate a region and so on. Basically, one thing that I didn't say is that, so in the first slide, when I presented how a training process is set up, so you basically compute the cost function, and you compute the gradient of the cost function with respect to the parameter that needs to be updated at each epoch. And this kind of setup, instead, to perform the Grad-CAM, or to extract the importance of the feature map, basically, you have to compute the gradient of your cost function, but not with respect to the parameter that must be optimized, but with respect to the feature map itself, to estimate the contribution to the gradient. And the idea is that a feature map is important if it gives a high contribution. This is what is behind Grad-CAM, state-of-the-art Grad-CAM ingredient.
Okay, thanks a lot.
You too, thank you.
Okay, let's see, do we have, okay, I don't think we have time for any more questions, so if anyone has anything else, please take it offline. And yeah, let's thank all of our speakers again.
Thank you very much.